Dear students, continuing with our lecture series on stereochemistry, this is our second lecture, and in the first lecture we have discussed about Graham's rule, whereas in this lecture we will discuss what are the details about Falcon's rule and what is its mechanism. Basically, the Graham's rule, which we have discussed in the previous lecture, you have seen that there are some drawbacks. Because of those drawbacks, we cannot sometimes predict the stereochemistry of the products formed. And to overcome those drawbacks, Falcon has given this model in 1968 for the alpha substituted acyclic ketones or aldehydes. As you have seen that the significant flaw in case of Graham's model was that the transition which led to the formation of products was an eclipsed conformation in the transition state between the alpha carbonyl largest substituent and the carbonyl substituent. That is, in case of aldehydes, this carbonyl substituent is going to be hydrogen. So the Falcon model has shown that the value of this R, as I have told you, this is H in case of aldehydes, and it can be an alkyl group in case of ketones. So as we increase the bulk of this group, changing from methyl to ethyl to isopropyl to tertiary-butyl, as we move down, the steric bulk of these substituent increases, and as the steric bulk increases, the diastereoselectivity of the product formed also increases. So this aspect is not covered in the Graham's rule. Graham's rule cannot explain that the effect of this R group in terms of steric bulk, how it will affect the diastereoselectivity. So Falcon model has that advantage also, that it can tell us that as we increase the bulk on the carbonyl R group, the diastereoselectivity increases. For example, when we do this lithium aluminum hydride reduction of this ketone, where R changes from methyl to ethyl to isopropyl to tertiary-butyl, as we know that the stereoselectivity or diastereoselectivity increases, we can see that we can have a syn product or erythro product and a therio product, and based on the transition state we will get the major product and the minor product. So this syn product or erythro product will be the major product, and this therio product or anti product will be the minor product. Now if we compare the transition states of both Graham's rules and Falcon's rules, you know, in Graham's rule we have this type of eclipsed conformation in case of the transition state, whereas these transition states they are just like reactants as far as Falcon rules is concerned. And then according to Falcon rules, the torsional strain which involves the partial bonds, which represents a substantial fraction of the strain between the fully formed bond when the degree of bonding is even quite low. Then if we differentiate between Graham's model and the Falcon model, here the conformation of the transition state is eclipsed conformation, whereas in case of Falcon's model it is a staggered conformation. So the stereoselectivity or diastereoselectivity of the products, that can be explained better when we consider that conformation in the transition state is staggered and not the eclipsed conformation as is taken in case of Graham's rule. Now, comparing these two models, if we see the Graham model, the eclipsed conformation, the nucleophile attacks at the perpendicular position to the carbonyl. Whereas when we take the case of Falcon model, here also the nucleophile attacks at the perpendicular position, but here the position of this R and keto, that is not eclipsed with the other substituent, but it is in the staggered form. So main steric interaction involving those around R and the nucleophile, but not around the carbonyl oxygen atom. So this is that if we consider the two possible transition state in case of Falcon model, then this will be the most favorable transition state, where there will be main steric interaction involving this R and the nucleophile, and not between the carbonyl oxygen and the nucleophile. So this conformation or this transition state will have the main interaction with the nucleophile. Then if one of the groups present on the alpha carbon 2 ketone is a electron withdrawing group. Now we know any electron withdrawing group will be electronegative in nature, and that means this will affect its interaction with the nucleophile, which is also electronegative in nature. So in such cases there will be a polar effect or electronic effect which will stabilize the transition state only where there is a maximum separation between nucleophile and the electron withdrawing, because both of these, they are electronegative in nature. So haloketones, where one of the groups present on the alpha carbon 2 ketones, either L or M, they may be halogen. So haloketones, they will not obey Graham's rule, because there what we will do is that, say if this group is a halogen group, and as per Graham's rule, in comparison to these three groups, H is smallest, halogen will be medium, and methyl group will be the largest. So therefore as per Graham's rule, methyl group will be anti to this carbonyl group. Whereas when we take the case of polar effect or electronic effect, then the halogen atom, that will be considered as anti-group, even if there is a larger group present in the molecule. So like this, the drawbacks of Falcon model is that here this cannot explain the formation of products in case of aldehyde, and this is because of the Falcon model assumption that the substituent minimization around the carbonyl R. So according to Falcon model, this is the favorable transition state for aldehydes, but this will lead to the formation of minor product, not the major product. So this can be explained by another modification of the Falcon model, which is called as Falcon-Ahern model. And Falcon-Ahern model basically is the elaboration of the Falcon model, which incorporates the improvements suggested by Ahern to correct the two weaknesses which we have seen in case of Falcon model. So as we have seen, the first weakness was that a strong polar effect in nucleophilic addition transition state, which will lead to the complete inversion of stereochemistry in case of SN2 type of reactions. So when there is an electronegative group present, then the polar effect comes into play as per the Falcon model is concerned. And as per Falcon-Ahern model, the uh, anti-periplanar effect as a consequence of asymmetric induction is there. So basically here what happens is that in case of anti-periplanar effect, this nucleophilic acceptor sigma antibonding orbital, this is parallel aligned parallel to both pi and pi antibonding orbitals of the carbonyl group. So this is how this can be explained, because this will provide stabilization for the incoming anion, and this can uh, quite easily overlap with the pi and pi antibonding orbitals of the carbonyl to have an effective overlap. So this anti-periplanar effect will determine that what kind of product will be formed in case of diastereoselective products. Then second weakness of the Falcon model, as you have seen, that Falcon model assumed that the substituent minimization around the carbonyl R, and this when this is applied to aldehydes, it was found that the product with the Falcon selectivity formed, they were actually the minor products, not the major products. So here what happens is that according to Falcon-Ahern model, the nucleophile will attack the carbonyl not at an angle of 90 but more than 90, and this angle generally which has been experimentally proved is larger than 90 degree and estimated between 100 to 110 degree, and practically this is generally 105 to 107 degree depending upon the substrate which we are going to use, having different types of R groups present on the ketone. And this angle which is more than 90 degree and close to 100 to 110 degree is called as Bouguereau-Dionys angle, and here the interaction between the nucleophile and the other groups is minimum repulsive interaction, so this will give a more stable transition state. And here also the homolume interaction between the nucleophile and the carbonyl will lead to attack of the nucleophile at an angle more than 90 degree, which is called as Bouguereau-Dionys angle. Now, if we apply this Falcon-Ahern model to aldehydes, so say we are having this type of aldehyde where at the alpha carbon we are having this smaller group, this medium group, and this larger group. And as per Falcon model, the larger group should be anti to the carbonyl, right? So this should be at the anti position and it should be perpendicular to the carbonyl group. Now, whereas in case of anti Falcon model, the attack of the nucleophile will be between medium group and the smaller group towards the medium group, whereas as for Falcon this should be at the side of the smaller group. So based on this you will get a favorable or unfavorable transition state. So favorable transition state will always be when the attack of the nucleophile take place from the side of the smaller group, that is the smallest substituent RS in this case. And if we see when in this molecule, if smallest group is hydrogen, say, then there will be minimum interaction between H of this aldehyde and this smaller H group and the nucleophile. So and this attack of the nucleophile will be least hindered trajectory, that is Burji-Dunez angle will be less sterically demanding in the transition state and will lead to the formation of favored product. So for example, if we take this aldehyde, you can see here there will be the smallest group, that is hydrogen. So if we have a Grignard reaction with this aldehyde, and you know the nucleophile in methyl magnesium bromide will be methyl group, and we draw the transition state of this reactant, then this H will be with the smallest group, and smallest group here is hydrogen, and then the nucleophile will attack from the side of the smallest group. So we will get this product with Felkin selectivity. Then another example is the effect of stereoselectivity or diastereoselectivity on the size of the nucleophile. So say in case of this aldehyde, 2-phenyl propionaldehyde, if we undertake Grignard reaction, and the R varies from methyl to ethyl to phenyl, and here again the favorable transition state will be where the nucleophile attacks at the Burgi-Dunez angle, that is at 107 to 110. This will take place from the side where the smallest substituent is attached at the alpha carbon. This is the smallest, this is medium, this is the largest. So largest will be at the perpendicular to the carbonyl. This medium is away from the attack of the nucleophile, and smallest nucleophile will attack from the side of the smallest group, and this will lead to the formation of major product like this. And the size of this nucleophile will determine that how much diastereoselectivity will be there. You can see as the size of the nucleophile increases, larger the size of the nucleophile, higher will be the percentage of the diastereoselectivity. So the products, they will be formed with high diastereoselectivity if this R group is a bigger group. Then few more examples. In case of ketones, those two examples we have taken last for of aldehydes. Now in case of ketones, say if we undertake sodium borohydride reduction of this ketone, 3-ethyl-4,4 dimethyl pentane 2-ol. Here you can see that this is the smallest group, this is the medium group, and this is the largest group. And largest group will be anti-group to the carbonyl, that is perpendicular to the carbonyl, so that they have the minimum interaction. And here the nucleophile is hydride, and this will attack from the smaller substituent at an angle of Burji-Dunez angle. So this favorable transition state will lead to the formation of this product, and we will get an anti-product with Falcon selectivity as the major product. Similarly, in case of lithium aluminum hydride reduction of 3s3-cyclohexyl butane 2-one. So here what we have done is we have replaced this tertiary butyl group by cyclohexyl group, so which is a even bigger group than the tertiary butyl group. And we can see that here again the favorable transition state, this bigger group will be perpendicular to carbonyl largest group, methyl is medium group, and this hydrogen is the smallest group. So nucleophile will attack from the smallest side of the smallest group, and this will lead to the formation of this anti-product as the Falcon selectivity product. Now the formation of diastereo selective products with anti-Falcon selectivity. So these types of products, they are generally formed in those substrates where we are having a non-chelating electron withdrawing substituent present at the alpha carbon, and if we are having these types of electron withdrawing substituent which are non-chelating in nature, say halogens, tertiamines or ethers as the substituent which are present at the alpha carbon of the carbonyl compound, then the products formed, they will be with anti-Falcon selectivity. Because here what happens is the nucleophile will add anti relative to the electron withdrawing group. Why? Because this is also a electron rich species, and electron withdrawing group is also more electron active, and they will repel each other. So to have the minimum repulsive interaction between these groups, so the nucleophile and the electron withdrawing group, they should be anti to each other. So that is why the transition state here will be a different transition state, which we call as the Falcon polar transition state. So here the halogen or the electron withdrawing substituent may or may not be the largest group, but still it has to be at the position anti to the attack of the nucleophile. So this will be the favorable transition state, and you can see that here the largest group is not the anti group, but anti group to the nucleophile is electron withdrawing group. So that is why the product formed will be with anti-Falcon selectivity, not with the Falcon selectivity. So if we go into the chemistry of these anti-Falcon selectivity, what happens is that say this is our carbonyl compound, and this carbon is the alpha carbon to the carbonyl system, right? And these are the three groups which are attached to the alpha carbon, and X is the electron active group which is attached, and these are the two other groups which may be smallest, or one group may be smallest and other may be either medium or it may be large in comparison to the halogen. Now the electron withdrawing group, say this one, this has low energy sigma antibonding orbitals. These ones, they can conjugate to the neighboring carbonyl group which is present, and this carbonyl group will have antibonding orbitals, and if an overlap is to take place, then the alignment of this carbonyl system with this X need to be right, and this alignment is right only when this group is perpendicular to X. So when electron withdrawing group is perpendicular to the carbonyl plane, then the carbonyl system is more reactive towards diastereoselective reactions, and because of that the uh, X group is taken as the anti-group to the attack of the nucleophile. So when the electronegative group is perpendicular to CO, then it is possible to get an overlap of pi anti orbital and sigma orbital of these two, and this will lead to the formation of products with more ease. Now we can explain these with a few examples. Now for example, if we are having this reactant 2-chloro 1-phenyl propane 1-O. Now this carbon is alpha carbon to the carbonyl, and here this is methyl group, and there will be one hydrogen which will be the smallest group, and this is the chloro group. And the most appropriate conformation will be where these halogen and the carbonyl, they will act as opposite dipoles. There will be least interaction between these two only when these are in the opposite position, so that means this should be perpendicular to this one. Now there are two transition states which are possible for this. If we go by FELKIN model only, then the hydrogen will be the smallest group, chloro will be the medium group, and methyl will be the largest group, and largest group will be anti or perpendicular to the ketone as per FELKIN model, and chloro will be the medium, and this will be the smallest, and the nucleophile, which is hydride ion in this case, has to attack from the smallest substituent side, and this will lead to the formation of this product, B product. But when we take into assessment the polar effect because of the presence of this halogen, that means this electronegative group has to be anti to the attack of the nucleophile, and it should be perpendicular to the carbonyl system, in spite of the fact that this is not the largest group present in the molecule. So with this assumption, this FELKIN ion polar model is to be considered, where this will be at the perpendicular position to carbonyl, and that should be anti to the attack of the nucleophile. So that is why here the major product is formed with anti-FELKIN selectivity, whereas the ratio of formation of these is 3:1. So if 75% of this is formed, 25% of this product with FELKIN model will be there, and 75% or major product will be formed with FELKIN ion polar model. Then few more example. This is the case of an aldehyde which is having this electronegative group present. Bn is benzyl, so N dibenzyl group is considered as the group which is responsible for the polar effect in case of this substrate. Now when the nucleophile is to attack as per FELKIN ion polar model, this group will be considered as the group anti to the attack of the nucleophile or perpendicular to the carbonyl system. So this transition state will lead to the formation of product with anti-Felkin selectivity. Similarly, if we take the example of this ketone, here the electronegative non-chelating group is this carbonyl group. This is smallest group. So this will be considered as group anti to the attack of the nucleophile or perpendicular to the carbonyl system to have the opposite dipoles. And here the nucleophile is methoxic ion, and this methoxy ion will attack from the side of the smallest substituent, leading to the product with anti-Felkin selectivity. So these are the references which have been used for preparing this lecture. Thank you very much.